So the next point, spatial data. What do we mean? What is spatial data? Well, we want to know where things are. We ask the question, where is something? Where does it exist? So we need to be able to place it somewhere in the world. Where we need to be able to say it's there, it's at a particular location. But actually this requires knowing where everything else is. Because nothing exists. There is no universal coordinate system. Everything is in relation to everything else. We cannot say that a particular point exists simply because of the universe. We are at a particular place on the Earth, but how we define that position varies depending on which coordinate system we are using, who we are talking to, and so on. So we need to know where perhaps not everything else is, but at least where other things are, so that we can relate a position to those. And we do this typically using coordinate systems. And these are tricky in some respects. We have to remember that our position on the Earth is partly not very well known. We can know it to some degree of accuracy. We may think we know where we are to a millimeter accuracy. But we exist on the Earth, which is a physical reality. It's an uneven surface. Not only do we have the standard topography of going up and down mountains, but the Earth bulges. It's an ellipsoid, an oblate spheroid. So this round object, except that it's deformed. It's not a perfect, a mathematically perfect object. Lumpy, but it's a potato shape, basically, is what is normally described as. And so our coordinate systems have to take this into consideration, and they are always a little bit of a lie, really. They can't be entirely accurate. They always have degrees of inaccuracy, and these will change throughout the day, throughout the year, depending on tides, depending on how much water there is in the ground, and so on. All of these small differences will affect your position, but hopefully not enough to be relevant for whatever it is you're doing. But how we represent coordinates, our position on the Earth, varies as well. We can represent our position as being on a mathematically perfect version of the Earth, this oblate spheroid or ellipsoid, where we have coordinates such as these, where we have degrees of longitude and latitude. So our latitude being here, we can go up from the equator by 60 degrees plus 40 minutes, 1 minute being 1/60th of a degree, and 6.61 seconds, 1 second being 1/60th of 1 minute, 1 minute being 1/60th of a degree. So it works very much the same way as seconds, minutes, and hours. Mathematically, it's very similar. And that describes our journey 60 degrees from the equator up north. And that ends us on this line here, or rather this line here, if we're actually looking at this. And then our easting from some point, some line of reference, which in this case is Greenwich in London for historical reasons. We move 17 degrees east, plus another 7 minutes, 7/60ths of a degree, plus nearly 7.9 seconds as a 60th of the next minute to get to this location. So this is our position in terms of degrees. So it's an angular position on the surface of this perfect, mathematically perfect sphere or ellipsoid. Well, that's good. That gets us with a minimum amount of distortion. We're ignoring the potato thing here, that the Earth isn't actually perfect. That gets us to this position, and that's as good as we can get. We'll say, okay, we can add on some more decimal places here and here, but that's a good position. It's not terribly convenient. I mean, we could represent these as decimal degrees. That absolutely, definitely happens, and the computer will often do that. But it's still degrees, and we're not very good. I mean, that changes depending on where we are on the surface of the Earth. How big is a degree? I mean, in terms of how many steps do we have to take to cover 1 degree? Well, that varies across the Earth. So it's not terribly convenient. What we actually want is some system whereby it measured in meters, for example. And typically what we will then do is project from the curved surface of the Earth to a flat surface, to a piece of paper, so that it represents, mathematically, looks kind of similar to what we experience in the everyday on our little part of the Earth, because it looks flat to us, generally speaking, on the surface of the Earth where we are locally. And so we project to a projected coordinate system, and in Sweden, the national grid covering the entire country is called SWIREF99TM. And so this is a map of Sweden projected using SWIREF99TM. It looks kind of familiar. This looks familiar as well, but here all I've done is I've taken the latitude and longitude, and which are in degrees, and I've just said 1 degree is equal to 1 linear unit of measurement as well. So it gets kind of flattened. And we can recognize that as maybe representing the curvature of the Earth. It kind of makes sense. But we can see it's not quite right. And we can't make any area calculations or distance calculations using this map. It's not going to work. Here we can. There are distortions, unfortunately, always when we project. I mean, this was already not quite true. The mathematically simple model on the ellipsoid was already a bit of a lie because of the potato. But then if we move even from there and project onto a flat piece of paper, it becomes even more of a lie. But it's still a lie that's good enough for us, as long as we're not using the map in an inappropriate way. What's inappropriate? That's a good question. But we have this map now where everything is represented as being a combination of linear distances that we can walk. We can step by step move along this, and it makes sense. If I take another step, we've moved the same distance along. Whereas with our angular distance, it changes depending on where we are, so that's not terribly convenient. So that's, but again, it's a more accurate representation of the physical reality of the Earth, whereas this is our convenient lie, this thing down here, this projected SWIREF99TM. And just to break things down a bit, the TM at the end here is telling us that this is a projection. When we get to the electron coordinate systems, we'll examine this more. So SWIREF99 is also a model of the Earth as a ball. A very specific model of in actual fact, very similar to this WGS84 ball model of the Earth. But we've taken this is a model of the Earth that is relevant for Sweden. And then we've put a piece of paper onto our model of the Earth and projected up to that piece of paper from the ball to the flat surface. And that projection is what we call TM. So this is our model, our flat model of the Earth. And when you're working with a GIS, certainly with ArcGIS Pro, if you're using that program, to get SWIREF99TM rather than SWIREF99, which will look like this, to get TM, which will look like this, you want a measured grid when you come to making your map. The computer's taking care of this for you. You don't need to worry terribly much about it. As long as all the metadata are correct and it's correctly informed about which coordinate system is being used, then all of this is taken care of by the computer, and you don't have to worry too much about it. But when you make your map, you will come to a point where you want to show on the map coordinates, and you want the measured grid of SWIREF99TM rather than these things, because these are good for storing the data, for doing certain calculations. They're good for surveyors and geodesists and people like that. But for most everyday purposes, actually we prefer this projected coordinate system. So spatial data also then isn't just about the position we have on the Earth. It's also on the flat surface of the Earth. It's also about the shape of the Earth and the relationship between objects. So our spatial data can represent things as topography, for example, the shape of the Earth's surface, which is the elevation, height above sea level, or the slope, how steep is the change in elevation, or the aspect, which way is that slope facing? Is it facing towards the sun or away from the sun? And then we have, going further, we have curvature. So how rapidly does that slope change? And in what direction does it change? As in, does it become less steep or more steep? So this is our curvature. the rate of change of this change. For those of you who are more mathematically inclined, you might recognize that. We also have topology, very similar word, very easy to confuse. Topology is another one of these words that we've borrowed in from somewhere else. As in, remember, I think back to ontology, we borrowed that in from philosophy, and topology we're borrowing from mathematics, and misusing it a little bit. But we're talking about the relationship between different parts of our data. And we also use it in terms of when it comes to making sure that the relationship between objects is correct for our purpose. It's a more active form of topology that we use in GIS as well. But it's still the relationship between objects. Do they touch or do they cross? That sort of thing. Does one contain another? So it's not reliant on distance as such. It's just reliant on the relationship between these objects. And when we combine all of these different things we've been talking about, we had our theory. We began way back, if you remember, we were talking about our theory, and we had nagged about metadata, and we actually have the spatial data, the things that are being represented on or being shown on the screen. And when we combine these, the combination of these different parts of spatial data, the combination when we have our images, so to speak, and we have the metadata describing them, and we have the theory that allows us to understand these things, that's when it becomes geographic information. It's not just information, and it's not just geography, it becomes geographic information. Where these intersect, that is what geographic information is. And whether we're talking about a geographic information system, which is a particular type of software, or geographic information technology, the T, where we gather in information, there's different aspects of it, we're still bound really by all of these things. The why are we doing this? How are we doing this? What's going to happen with this? These are all connected to our geographic information.